In section 6.6, we talk about frames and machines. So let me just put this picture in here. This is a frame. So a frame is a structure where at least one member is a multi-force or multi-moment member. So if we look at this structure I have here, I'll have a weight hanging from this pole, and it's buried in the ground here at A. Label these C and D. This point, we can call it E. So like all structures, I can create a free body diagram of the entire structure. And we'll do that. Get rid of this down here. So I'll have a reaction AY here, AX, and then we're going to have a moment here since this is fully supported. And then over here, I have a weight, W. So the way we're going to solve this is I'm going to first dismantle every piece, every member, and draw a free body diagram for it. So this one, we have point C and point A, and I guess this is point C, this is point B. And then I'll draw my loads on that. So I'm going to draw C in this direction, CX. I have a CY. I have B. I'll go with a tension in that member. Force B. I guess this is BD. And then, again with our reactions, AY and AX. So that's a second free body diagram I have to work with now. Notice I recognized member BD is a two-force member, so I just drew one force for it. Okay, member CE, then I need to draw my forces. So let's start out, we have a weight here. Now, when I draw my force at B, I need to draw it in a way that's going to oppose what's going on here in BD. And that's going to be actually more apparent when I draw the angled member. But over here, let's show you what I mean. I need to have CX be drawn in such a way that it opposes CX in my other free body diagram, and CY has to oppose CY in the other free body diagram. Otherwise, there's not equilibrium at that point. So you don't want to draw, when you're drawing multiple free body diagrams, you want to make sure that your reactions at a link point are opposite each other. Okay, we have one more. I'm drawing this down here. Probably drew it bigger than I needed to, actually. That's fine. So this is link BD. So this is B, this is D here. Oops, didn't want to erase that. I wanted to erase this. This is D up here. And again, I have to oppose the force in the BD up here, and I have to oppose the force in the BD down here. So it's drawing as if there's tension in this member, although that's not necessarily going to turn out to be the case. So it's important enough, I just wrote a little note here, that all the opposing forces are drawn equal and in the opposite sense to maintain equilibrium. And for analysis, just want to point out we have up to 3 independent equilibrium equations per member to use in our analysis. So I might, for example, I might use free body diagram 3 and some forces about C, so that if I knew what the weight was hanging off the end, so that I could find the force FBD. Of course, I'd need to know the direction. I have to have enough information to know the direction that force is pointing. And then after that, I could use that to find my summing. I could then sum forces in the X and the Y direction to find the CY and CX. I could, yeah. So here's our problem. We have a 600 Newton load here, and we want to figure out what's the force at P to hold this in equilibrium, and what is the tension in the cables. These are frictionless pulleys, by the way. So let's draw some free body diagrams. Let me use the ink to shape here. And so our first pulley looks something like that. We have a, let's do them in green, I guess. I have a reaction here, or the force in that line. I have P here is the tension in that, and since this is a pulley and it's free to rotate frictionlessly, we have also P over here, and then I have some tension pulling down here, T. So there's free body diagram number 1. Let me do some more. Free body diagram number 2. If I number these, I'll be able to refer to them. Okay, this one's a smaller pulley. Looks like about this big. And we have then a opposite load here, opposing this, of T. And then we have 2 forces here. Let's come back to these, I think, because I see that this and this should be the same, which means that is P then, and if that's P, this has to be P. Okay, I guess we don't have to come back to it. We can just talk about it now. And then finally, a little bit bigger pulley. This one has a force here pulling up. It has a force here of P and a force here of P, and then we're loaded. Our load is on this guy, or 600 newtons, and that's our free body diagram number 3. So from inspection, I can see that if this guy here is P, then I have to have equal and opposite. That's like our first rule. P here, facing up against it. Okay, opposing it, I guess I should say. So let's analyze this thing. So from free body diagram number let's see. Looks like we can figure out what P is from free body diagram number 3. So from free body diagram number 3, I have sum of forces in the y direction equal to 0 equals 3P. Yep. All right, so it crashed on me, loaded it back up. So I have 3p minus 600. Therefore, p equals 600 over 3, or 200 newtons. Okay, now that I know what P is, I can use free body diagram number 2 here. And I can again sum forces in the y equal to 0. And here I have 2p, or minus 2p, plus t. Therefore, t equals 2p equals 400 newtons equals t. So that's all I needed to do. So that solves the problem. I could find the reaction at C with the first free body diagram. I could again sum forces in the y equals 0, and I'm going to get RC minus 2p minus t, and that's going to end up, if you do the math, 2p is 400 and t is 400. That means that RC is holding a load of 800 newtons. Wasn't required for the problem, but we can do it anyways. It's a neat optical illusion. It made it look like that rotated. So that's a simple problem.